No, because this is also negative. Yeah, but you had me there for a second. No, if we add together a sum of positive terms and it gets away from us, it is going to blow up to infinity. All right, so. All right, so, oops. What I have to show you guys for the rest of class, I need to use the projector for because it's a little bit ugly. Okay, it's a lot ugly. And it touches back on integration, so I want to make a connection. I want to make a connection with your other course. I mean, Calculus 1, right? And in particular, well, first of all, I've got a silly application of the geometric series. You know, one of the so here's one of the stupider things I've done as a teacher. I taught the geometric series once in college algebra. I did that.
How well did it go over?
Oh, they loved it. Yeah, they were like bowing down to me. They were like in the middle of my lectures. They were like, "Preach it, brother." You know, like it was epic. No, they hated it with a pure and unbridled hatred.
Why? It's so simple.
Of course, but that was when I was first here, like 2009-ish maybe, and it was a large lecture section of college algebra in a room which I think is now like Cassis. The first floor DeMoss. You know, how many times has DeMoss been remodeled since I've been here? I don't even know. Enough, I guess. I would just point out, I have another example of telescoping series in the notes for you to look at if you want. It's kind of the same thing, but this one it has the bookends of it, if you will. The telescope doesn't smush all the way down to two things. It leaves two things on both ends sticking out. So, so there's that. Not especially interesting, but geometric series, we were just doing that. Here's the theorem stated formally that we just proved. Namely, this geometric series is convergent if and only if the radius of the series is, you know, absolute value less than 1. Just gotta zoom out a bit. There we go. We're good. So you're getting back to my college algebra idiocy. So you can use the geometric series to take any decimal with a repeating fraction and convert it to a fraction of numbers. Like this, essentially the geometric series is part of the proof, if you will, or you could use it to form the proof that any real number with a repeating decimal has to be a rational number. It's the fraction of two integers. All right. If there isn't a repeating decimal, then it's an irrational, like pi or e, things like that. All right. And then I have this stupid example. A man and infinitely many of his friends go to a hot dog stand. The first man wants a whole hot dog. Then the second man says he'll take half a hot dog. The third man says he'll have half of a hot dog. The fourth asks for an eighth of a hot dog. The first man is going to pay the bill for this infinite order. How many hot dogs does he need to buy? So this is a geometric series. See, because he's the first hot dog, then half, then a quarter, then an eighth, and so forth and so on. That is a convergent geometric series with c equals to 1, r equals to 2. And the answer is he needs 2 hot dogs, right? Now, if we were not at liberty, then these would not be hot dogs. This would not be a hot dog stand. This is typically, well, anyway, this is not the usual form of this example. So if you want, I'll tell you in office hours the usual form. What? No.
I'm just confused.
Wait a minute. Are you? There's no drinking, right?
No drinking.
No drinking. Okay. Good. Okay. Okay. So moving on. Let me remind you, the Riemann integral. Did you already, if you think about it, you already faced series. How did we define the Riemann integral? It was the limit of a sum. It was an infinite sum, was it not? That's a series. We use series to define the integral. But it's a little bit twisted. It's a little bit twisted. Let me explain to you. It's a lot twisted. But my point to you is that, so think about this. Here's a really, so these are the worst homework problems. And these are in Stewart, all right? And I don't know, I may or may not have actually put one in your homework. I probably did. That seems like me. So think about this. If you can look at the series that you're given and recognize it's the Riemann sum for an integral that you can do, then you can calculate the series by doing the integral. Like, what? Yeah. Because I basically can go from here back over to here where I can do that, right? Let me make it explicit. So here's an example. Find the limit as n goes to infinity, I equals 1 to n of 1 plus I over n, quantity squared, 1 over n. So, okay, so first of all, if you see something like this integration trick I'm telling you is the only way, pretty much, to deal with this kind of monstrosity. This is really, really different than every example I've showed you. Every example I've showed you has been formed what? Sum k equals 1 to n, right? Or k equals 1 to infinity. But when we look at the partial sum, it's sum k equals 1 to n of a sub k, right? Okay, what's a sub, so here I used I. What's a sub I? You can't tell me because it's got the n the n is in here, it's messing with you. This is not explicitly of the form sum I equals 1 to n of a sub I. So the weird thing about these examples is to even figure out what a sub I you're summing, it takes work. But let me just focus on how to calculate here. So if I look at this, I tilt my head and squint and go, oh, it's a Riemann problem. So the thing out to the side probably is my delta x. And the thing inside is probably my x sub I. So there's lots of choices, but just make one. So I'm going to make delta x 1 over n. And so if we can set a equal to 0 and b equals to 1, that's a good way to get 1 over n for my delta x, b minus a over n. Then I'm like, okay, well, if my delta x is b minus a over n, this is 1 plus I delta x, right? So in other words, oh no, I just said that the x sub I was this. There are other choices. So I identify that my 1 plus I over n is actually 1 plus x sub I. All right, great. And so, all right, lovely. Then this, oh, come on. Why did I get a cube there? Really? Son of a gun. Well, I got to fix this. Make that a cube, make this a cube, then we're fine, okay? So I somehow, somewhere mid calculation, I changed 2 to a 3 because I'm an idiot. But anyway, if you do this, look, Riemann sum, woohoo! So we know how to do that. We integrate. Calculate the integral, 15 over 4. This is the third way to calculate a series. But the series that you can calculate with this method are of a really weird form. So here's another one. Well, let me just talk about that then. What is the nth term? You could figure it out using the proof for the nth term test. Because the nth term test did what? It told you how to get from the partial sum back to the thing you're adding up. So this one, I manifestly have the formula for the nth partial sum. It's this. Again, I need to put that to be a 3. Sorry. And, oh man. Rats. Well, I'll fix it. None of you have printed it yet because I haven't shared it with you, so it's safe. But anyway, so this is the n minus 1th partial sum. So here's the formula for a sub n, which you could actually work out using those Gauss sums. you could actually work it out using the Gauss sums. I think I have a simpler example of this, but here's another one. If I wanted to calculate this series, I go, oh, okay, so I'm going to make my delta x, let's see here. Well, I decided I want this to be the x sub I, all right? So if that's going to be the x sub I, I'm going to make that like a plus I delta x. So tilting your head and squinting, I see a equals to 0. My delta x is pi over 2n. That means that I want my b to be pi over 2. And so to make the delta x over appear, I have to convert this 1 over n to like 2 over pi times delta x. And anyway, I work it out. I get 2 over pi. So, So I wanted to give you a couple of examples of these because they're really, really weird. I think these examples are pretty contrived. I think they only exist in calculus books as far as I know. But I do think this is worth talking. Like I said, I don't think those examples are found in the wild. But this proof I'm about to show you is very much natural, and I think it's important to see. So the proof I gave you of Fundamental Theorem of Calculus Part 2 on day 1 or 2 in here, we did not use this argument. We used a argument about like we had two derivatives. If two derivatives are equal, they have to be equal up to like shift by a constant, right? The functions have to be, basically it was if f prime of x and g prime of x are equal, it means the f of x is equal to g of x plus a constant. One of those was the area function. We took the difference. We found the f of b minus f of a formula, right? No series were in sight. You can actually derive FTC II, though, if you use this argument. So essentially, if you have an antiderivative for your integrand, right, that means that big F prime of x is equal to little f of x, right? So if you apply the mean value theorem on each subinterval, you can rewrite the difference of the antiderivatives. What is f prime? Since it's the antiderivative of little f, this is little f of x. So if you look at this, what we really have is that, here it is, f of x1 star delta x is the difference of the antiderivatives at the endpoints of the first interval. And this can be done on each subinterval that you're forming the Riemann sum from. And so here's the calculation. The Riemann integral is equal to this summation, right? I choose the sample points to be the points suggested by the mean value theorem to replace f of x times delta of x by the difference of the antiderivatives. But then when you add those up, it's a telescoping series. Actually, this one, it doesn't even have an end dependence. It just always ends up with f of b minus f of a, which gives you this. So this is a really very different way of understanding the Fundamental Theorem of Calculus Part 2 than I showed you at the start of the semester. And that's part of the reason I think it's worth spending time talking about how the Riemann integral itself is a series, all right, in this sense. But it doesn't make for natural problems. So that brings us to the next thing, which is convergence and divergence theory. So I told you there's 4 ways. The other way of calculating the sum of a series, we actually need power series to do, so that has to wait till later, all right? So what starts next time is our tour through methods of convergence and divergence. So far today, we have 2 main methods, 3 actually, I would say. The 3 main methods we should have learned today are the nth term test that makes it diverge, all right? Geometric series test is huge. A lot of times we'll face a geometric series. And then the third, I would say, which is more or less a method, is recognizing telescoping series, all right? This thing I showed you about the Riemann integral at the end, it's kind of a wackadoodle example. I mean, I want to talk about it, but it would probably appear in homework. I'm not sure it would be a reasonable test question necessarily. Maybe a bonus, but yeah. Anyway, watch out for the CFAWs. Oh, you got it?